the heating curve. This is chemistry lesson number 13. The heating and cooling curve. So first let's draw the heating curve. You may have seen this, you may have not. Most importantly, let's first draw the x-axis and y-axis. The x-axis is internal heat in joules, and the other axis is temperature in the form of Celsius. In America, we use Fahrenheit, but everywhere else in the world, we use Celsius. So, let's make this point. This is obviously below 0, as this is 0. Let's say this is 100, and this is over 100. That's obviously true, so you don't need to write that. First, ice starts at way below 0. Then, when you hit, it starts to melt as it gets to 0 degrees Celsius. Now, its face is changing. It has turned into water. So, Q1, Q2. Next, we'll go up to Q3. So, Q3, then the steam heats up from 100 degrees to even higher degrees. Such write the information we need. So we need 334 joules to get ice to transform into water, and we need 2,260 joules. Wow, that's a lot to boil water into steam or water vapor. Now let's make a table of what's happening in the equations. So, this is all we need. So, this is Q. So Q1, Q2, Q3, Q4, and Q5. This is the explanation or what's happening in the heating curve. So, at Q1, ice is starting to melt. Ice is starting to melt into H2O. So it completely melts into H2O. So there's a phase change. Ice becomes H2O. So what happens in Q3 is H2O starts to boil. And in Q4, H2O becomes steam or water vapor. Q5 is what happens at Q5 is steam heats up. Now let's write the equations. Q equals MC, the capacity for ice, since it is ice for this one, delta T, which stands for the change of temperature. The phase change here, so now Q is the mass times the change of heat fusion, which is 334 here, as I showed you. Q and M can, again, only this time the capacity is for water, since the water is heating up, but not the ice. And Q4, it should be delta H vaporization, which is here, water vapor. And now when the steam heats up, it's the heat capacity of steam, delta T. You may already know the heat capacity for water, but you may not know the heat capacity for ice, which is 2.03, or the heat capacity for steam, which is 2.01. You'll need those if you're solving a problem that involves a heating curve. You can use it in the cooling curve. Now let's do the cooling curve. Don't say this had to be bigger. So, as always, let's first draw the X and Y axis. So, as always, internal heat in joules and temperature in Celsius. Okay. So this is below 0. This is 0. And this is 100. And this is above 100. Q5 becomes Q1. So this is Q1 now. So it goes back from a higher temperature to 100 degrees Celsius. Now, we're going to draw this part. Q4 becomes Q2. Of course, it is still as long as it was before. Man, losing all the energy, the heat energy of steam takes a very long time. It's a very lot of energy too. So, the Q3 goes all the way back to 0, like it goes from 0 all the way to 100. So I'll circle this part since that's what I'm drawing. This Q2 and became Q4, and Q1 and became Q5. Don't worry, I go to circle that. Okay. This is the cooling curve. This is the heating curve. Little signs to remind you what Q5 has became Q1. Q4 has became Q2. Q3 is still the same. It's still Q3. Q4 Q2 has became Q4, and Q1 has became Q5. So the heating curve, everyone who's watching, is basically the opposite of the cooling curve. Thanks for watching, and I hope you subscribe to Berry Science Lab for more videos.